Hello everyone. Good morning, good afternoon, good evening. Take my greetings according to your timing. Now I would just continue the lecture number 4 for the stereochemistry. So before going to the next topic, I would just make you revise of the previous topic that we have already learned, the RS nomenclature. So in RS nomenclature, we have get to know about the CIP rule and everything. So I think we need to practice a single question and you will just recall all the concepts that I have taught you in my last lecture. So let's take one example. Okay, just give me a second. I'll just skip this one. Okay, if I'm solving this, so what are we having over here? We are having bromine, and here we are having OH group, alcoholic group. We are having CH3 group over here and hydrogen. So clearly you can see that the lowest priority will be given to hydrogen. Fourth, done. Then which will get the next priority? Then we are having oxygen and carbon. You know carbon is of 6, so it will have the next priority. Then this is going to be 3. Then you know it is bromine and this is oxygen. Obviously bromine is 35 atomic number, so it will have the highest priority. So bromine will get 1 and OH will get 2. So this is the whole sort of thing. Now the whole point is that how will you see how the rotation is taking place? See, you will have to move from 1, 2 and 4 over here like this way. So this is what? This is a clockwise rotation. Generally clocks rotates like this way. See, this is the rotation. So as the rotation is like this, then this is definitely going to be what? This is definitely going to be about our nomenclature. Fine. Next, we have our next question as this. Just a second. Here I come with the next question. See, here another rule that I have taught you, that if the carbon means like if the joining atom to the main carbon is same, see here this is carbon, this is carbon, this is carbon, then we are going to see the next adjacent atom to it. This, in this case this. So this is how it's going to happen. So clearly this is going to be 4. So I have marked H as 4. Then CH3. CH3 what we are having? We are having like this way. 6. Then we are having 1 comma 1 comma 1. Fine. Then in CHO what we are having? 6 for carbon. Then we are having 8 for oxygen, as there is double bond, so 2 8s for 2 oxygen, and it is 1 for hydrogen. I'm going to show you how it's happening. So if I will draw the structures, this is CHO. Okay, so CHO can be written like this way, that it is C double bond O and this is H. Okay, if we don't think about this double bond, then we can also write like this way, that this is carbon and here you come with OH. Okay, and here you are having, sorry, okay, see here as the double bond is present, so here I will add one oxygen, here I will add one other oxygen, this is hydrogen. Okay, when we just clearly split the bonds, and let's go to CH2OH, then what is the structure of our CH2OH? CH2OH. Fine. So CH2OH can be written like this way. This is carbon C, this is hydrogen, and here I am having OH. Fine. And then we are having what? We are having CH. This CH3 is very basic. I'm not going to do this. Okay, fine. Let's do it. CH3. Okay, CH3, how will you write this? Just C and hydrogen. Okay, fine. Here you can see the complexity. The complexity will tell you how it's going to happen, and in this case what will happen, this is will going to continue 6 comma 8 comma 1 comma 1 comma 1. Okay, so this is the whole thing. So you can see how the numberings are given. So clearly now you can mark that which one do you need. This is 4, then this is going to be CH3 going to be in the third priority, then CH2OH is going to be our second priority, and CHO will get the first priority. So as it get the first priority, we will just try to draw the whole thing. See, here is our 1. We will have to move through 2, 3 and then 4. Here I move through here, and it's an anti-clockwise direction. So this is our what? This is our S nomenclature. Okay. So I think this two questions has recalled you how we use the CIP rule. So without further any kind of delay, let me move to our today's topic. That is the resolution of racemic modification. And by the meanwhile time, I would just get into the topic and let you know about the geometrical isomerism as well. And today's target is to complete the whole thing that is left for stereochemistry, because these are the minor parts. We have already covered the main part and chiral drugs as well, so it would need just a few minutes. If the lecture goes long, I would request you to be patient, and I will try to complete it as much time as I can take in a most briefest way I can. So let's come to the topic. Okay, so our topic is resolution of racemic mixture. So resolution means basically separation of racemic mixture into its constituent enantiomers. So I know what is racemic mixture. I have already taught you. If you can't remember, so I just get back to where I have taught you racemic mixture. See, here is the definition for the racemic mixture. An equimolar mixture of D and L form is known as racemic mixture. Racemic mixture is optically inactive in nature due to external compensation. Fine, I have already taught you this, and this is the last time I'm saying what is racemic mixture. Just remember this term racemic mixture, because it's going to come again and again repeatedly in upcoming forms. See, so we are having racemic mixtures, and now it should be broken down into enantiomers. Enantiomers, I hope you remember, purification of enantiomers are much needed, because 50% of racemic mixture is present in the enantiomer. So what is the method? First method is the biochemical method. In this biochemical method, I would just discuss the process, and then I will go for the pros and cons. So basically in this process, this solution of racemic mixture is taken. So this is a racemic solution of racemic mixture. Then certain bacteria and molds are allowed to grow in this solution. Certain chemical specific bacteria are used, to be very specific. Okay, bacteria and molds grow. Then this bacteria destroy one enantiomer selectively, leaving the other. Fine. So that means this bacteria should be very much specific about what enantiomer we need. Okay, this is actually chemical specific. Okay, then what are the drawback of it? Listen, once we are destroying something, it will create a drawback. So if we are one enantiomer always get destroyed and one is received, which is not actually reliable. We are just destroying it. Why should we destroy it? Maybe we can just separate it out. That would be more beneficial for us. So another thing is that difficulty to find such enantiomer oriented organism. Okay, fine, which I have told you, this bacteria should be very much specific. So next, chemical method, and I'm giving it a 300, means like 3 stars, because the method which is actually used in laboratories is chemical method, and we generally use it in many, means like this is the most commonly used method. So what is the most commonly used method? If anyone will ask you, you will just say it's a chemical method. So what's the process? The process is that the racemic mixture consists of R and S. Okay, so if it is having R and S, so this S base is added to the mixture. Again a S base is added to the mixture. R and S acid is present, and there we add a S base. If we add this S base, it will form a diastereomer, and you know what is diastereomer, right? Having different physical and properties like boiling point and melting point. Okay, due to this different physical properties, it can be easily separated by fractional crystallization and fractional distillation. Fine. How it's happening? This is our RS salt and this is our SS salt. We are just pouring dilute hydrochloric acid to it, and then we are getting R acid, S base HCl, and here we are getting S acid and H base HCl. Fine. So next is our preferential crystallization by inoculation. So what was the process? So we will have to take a super saturated solution of racemic mixture. Okay, what is super saturated solution? I hope in class 11, 12 you have written, means like you have read that what is super saturated. Super saturated basically means when you means like after a certain point of time, when you can't add any more solvent to the solution, then it is considered as the super saturated solution. Fine. Then seeded with a crystal of one of the two enantiomers. Okay, see, in this supersaturated solution we will add the crystals of one of the two enantiomers. This induces crystallization of the added enantiomer. The thing which we will add, means like the crystals which we will add, will just induce the crystallization of the added enantiomer in the present racemic mixture. This is the process of inoculation. Then coming to the kinetic method. So some of the enantiomer of some racemic mixture react faster than the other. With this we can do what? We can with an optically active compound. So with an optically active compound, if one enantiomer is basically taking faster, means like faster reaction, then we can just do what? We can just inhibit a reaction and get our desired enantiomer. And lastly, the chromatography. So optically active compounds may selectively be absorbed by some optically absorbed chiral absorbent. Okay, so coming to the next topic, which is our geometrical isomerism. From exam point of view, I would just suggest just remember a short note about geometrical isomerism, because it may also come. So let me dive into what is geometrical isomerism. Compounds having same molecular formula, same structural formula, but different in arrangement of atoms or groups in a space around the double bond is known as geometrical isomerism. So what are the key highlighting points you are having here? Same molecular formula, same structural formula, and different arrangement of atoms or groups in a space. So this is the 3 point. This is point 1, this is point 2, and this is point 3. Fine. Now, so, and this is called geometrical isomers, and this phenomena is called as geometrical isomerism. Fine. So what is the condition for geometrical isomerism? First condition is that compound must contain a double bond. This is the must thing. Okay, the atoms or groups attached to same carbon atom must be different. Fine. Now, so how does this origin of this geometrical isomerism comes? See, when you are having a linear compound, this is CH3, CH2, CH2, CH3. Okay, you can't see any double bond. So here this rotation around carbon single bond is possible. Okay, but when CH3CH double bond CH3 is there is a double bond present. Due to this double bond, what happens? There is a restriction of rotation around this double bond. This has initiated the topic of geometrical isomerism. Fine, we get two types of geometrical isomerism, or you can say the two ways we can say in geometrical isomerism. One is our cis trans and another one is our Ez. Okay, so what was cis trans and what is Ez? In cis trans isomerism, basically the groups present in it will be same. It's like the two groups to the adjacent carbon atoms may be same. Okay, it means maybe same, not it will be same. Okay, so this is, you can see this is a group A, this is group A in two adjacent carbons. This is group B, this is group B. But in Ez, means like nomenclature, you will see none of the groups are same. This is A, this is B, this is X, and this is Y. Fine, we will just get into the deeper portion of it. Just stay concentrated over here. You just read with me once, and I promise you don't have to remember this. You can just memorize this notes one day before your exam. So, cis-trans isomerism. When similar atoms or groups are present on same side of the double bond, then this is called as cis isomerism. Here you can see CH3 on the same side. Okay, and hydrogen on the same side. Actually, if we draw the plane, so you can see this is CH3 and CH3 is above the plane and H is below the plane. Okay, This is one example. What is the structure of this? Is actually cis-2-butene structure. And let me make you remember one structure, that is our malic acid. What is malic acid? Here you can see the two carbon atoms attached with COOH acidic group, COOH in the C's position. This is called as malic acid. Okay, what is trans isomerism? When the similar atoms or groups are present on the opposite side of the double bond. See, here is the CH3 and here is the CH3. If I draw the linear plane, you can see one is above the plane, one is the below the plane. So this is our trans 2-butene. And when this malic acid is in the trans form, it has been known as the fumaric acid. What did I say? I just said that when this malic acid has been means like malic acid is present in trans isomerism form, it forms the fumaric acid. Fine, we are done with our cis trans isomerism. Now come to the EZ nomenclature. So EZ nomenclature, I would just say that when all the groups attached to the C double bond C are completely different from each other, then it is EZ nomenclature that we usually use. So the priority across carbon atom is checked by using CIP rule. I hope you remember CIP rule. Here I am not going to repeat the rules. If you want it, just previous lecture only I have taught you. Go through those lectures and you will just recall it. Okay, come here. So next we are having what? We are having carbon, carbon. How will you specify the priority? Here you can see in one carbon is attached with A and B, another carbon is attached with X and Y. You have to decide the priority between A and B first, then X and Y first. Then if you will see that this A is having higher priority, let's say this A is having priority 1 and B is having priority 2. Okay, and this X is having priority 1 and means like Y is having priority 2. So here you can see, okay, let me, here this is having priority 1 and this is having priority 2. This is having priority 1 and this is having priority 2. So this you can see that the priority of 1 is lying in the same plane. So you can say that this is our Z configuration, because Z means this EZ configuration, the word has been taken from the German, coined from the German words. Z means zusammen, that means together, and E means antigen, that means across or opposite. So as you can see in, like if I draw the plane, you can see A and X with same priority are on the same side. So this is definitely going to be what? This is definitely going to be our Z configuration. Fine. And if wait, I'm just correcting it. This is not 2 anymore, and here comes, okay, I'm erasing it. Okay, if it is 1 and Y is 1 and X is 2 and B is 2, okay, B is 2. So you can see, if I will draw the plane, the priority here, 1 lies above the plane, Y lies below, A lies above the plane and Y lies below the plane. So you can see opposite like the trans. So this is coined as our E configuration, the antigen E configuration. Fine. This is all about our EZ configuration. So here we are completely done about the EZ nomenclature, and coming to our very last topic, that is our chiral drugs. What is chiral drugs? See, according to exam point of view, I would just say remember its example and you are done. But as I'm teaching it thoroughly, so I would just get deeper into its theory. But you don't have to recall each and everything. Just remember what am I telling you. That's it. Okay. See, what are chiral drugs? Before knowing what is chiral drugs, let me recall you what is chirality. So chirality is the property of a molecule where its spatial arrangement of atoms cannot superimpose on its mirror image. Okay, our hands are not superimposable on each other. Okay, that means they are chiral in nature. See, drugs that exhibit handiness, that means ability to classify chiral objects into right-handed or left-handed objects, are referred to as chiral drugs. Fine. Next, biological systems like that of human beings have been known to exhibit chirality. Thus, it reflects existence of chiral specificity on drugs. In human body, we are having a system that actually can detect that this is right-handed, this is left-handed. So we can say that our body is chiral specific in nature. And this kind of drugs are actually equimolar in nature. Okay, an equimolar mixture of enantiomers. Basically, what does equimolar mixture of enantiomer means? That means racemic mixture we are having here. Okay, our body is chiral selector. It interacts with each racemic drugs. Okay, each racemic drugs differently and metabolize each enantiomer by separate pathway to generate different pharmacological activity. Okay, thus one isomer may produce desired activity while the other may become inactive, or in worst case scenario, like in the means like in our in the very first previous class, means like in our my lecture 1, when I started this whole thing, I have already told you about the thalidomide disaster. So actually it means that in worst case it can produce some undesirable or toxic effects in the body. So, why is it important to get this chiral drugs? Basically, in pharmaceutical companies, 56% of the drugs currently in use are chiral molecules. Okay. And 88%, see the numbers, 88% of it are racemics. That means they are racemic in nature. So, these are the importance why we need this kind of chiral drugs. And finally, we will end this topic with two examples, that is our thalidomide that I have already discussed and ibuprofen. So, thalidomide relieves anxiety and it gives you drowsiness, but in S, it causes birth defect in child. And ibuprofen R is totally inactive. Okay, and ACE is used as painkiller. So I have completed the whole stereochemistry in only 4 lectures. Go through those all lectures, and I will try to conduct some PYQ sessions regarding each and every topic. Meanwhile, thank you, and if you have any doubt, don't forget to comment in the comment box. And next means like next lecture would be of might be spectroscopy, and I hope you will also follow them. So meet you in the next session. Bye bye.